Well, as Eamon just said, my name is Stacia Van Zetten, and I work for a company called Exact Technology. But more importantly, I'm filling in today for Mitchell Mateus, who works for Topdown Construction up in Toronto, Canada, which is actually where I used to work. And one of my last projects was working on what this presentation is about. So I guess I'm an appropriate substitute for him today. So this presentation is going to discuss the research and development towards a proposed solution to overcome constructability limitations of mass concrete structural walls for the Eglinton LRT project in Toronto, Canada. I'm going to quickly discuss the project that initiated the discussion for this topic, explain the obstacles that we've had to overcome, go through the details of our trial program to prove out a mix and the methodology, and then finally finish with the next steps. So here's a map of the project in question, the Eglinton LRT in Toronto, Canada. The LRT is, just to mention, most of my units are degrees Celsius and meters. So the LRT is being built by a design and construction consortium called Crosslinks, which is comprised of Dragados, Acon, SNC-Lavalin, and of course, Elliston. There's over 19 kilometers of new light rail, 10 of which is underground. And most of the concrete placed on the project is considered mass concrete, including the foundation walls, which can be up to 1.5 meters thick, and slabs up to 2.5 meters thick. We spent about a year between 2015 and 2016 pushing the specifications to allow for a higher percent supplementary cementitious material in the mix. Originally, it was dictated by the specs to have 49% slag replacement maximum, but after many meetings and durability trials, we were able to increase this limitation to 70%. We worked with 3 concrete suppliers on the project to test and develop a conventional mass concrete mix that would give us the most latitude to pour in various conditions. Then we ended up providing the teams with a thermal control plan similar to these tables, to visually display the various conditions and what maximum temperatures and differentials they can expect. This is for a conventional mix. And then after a year of construction, the site teams recognized that some of the roof slabs were heavily congested with reinforcement and conduits. So a self-consolidating mass concrete mix needed to be designed as well. This is actually something I'm going to be presenting at the spring 2022 convention. But the same procedure of testing and developing the mix designs was done. And then come later on, I guess it was 2018, where we realized we needed to shoot some of the walls. Unlike the mixes that were already approved, the Shotcrete mix and the Shotcrete method in general is slightly harder to prove out. A handful of the stations are going to utilize, or are now currently utilizing, the top-down method of construction, which means first construct the roof slab and then excavate below and build the stations underneath there. The pictures show the beginning of this process. The one on the left here is the mud slab, and then the one on the right is the roof slab, which is tarped. Top-down construction allows work to proceed below and above that slab at the same time once it's gained its required strength. That means that the road will be able to reopen while construction continues below, ultimately being less disruptive. Anyone that lives in the area, though, would probably not agree with that. It's chaos. So top-down construction also comes with its challenges. In some of the stations, the main concern was brought up by the formwork subcontractors, that the strategy for conventionally forming around the support struts with the roof in place made constructability a nightmare. They considered the option of putting in gantry cranes running across the roof and the suspended slabs, but ultimately decided that using structural shotcrete for these foundation walls would be the most efficient solution. Unlike the mixtures that we already accepted, additional considerations were needed when developing a shotcrete mix, mainly the stackability of the concrete. And then a fun wrench that was thrown in by the Shotcrete contractors was that they typically can't shoot a mix with more than 20% slag, as it's really hard to keep that stackability. So 20% is really far from our desired 70%. So we knew that we had some work ahead of us. So a 3-phase research program was carried out to select a shotcrete mix that would meet all of the specified durability parameters, maintain the low heat of hydration requirements for mass concrete, and be pumpable, shootable, and stackable. So what were we looking for in phase 1? We tested 26 different shotcrete mixtures to select the best performing mixtures to run through the shooting process. The mix designs were tested against each of the 3 ready mix suppliers' baseline control mix, with very tight temperature limits, large elements, and being restricted to a high volume of cementitious content. We knew we had to make a 70% slag mix work, even though it hadn't really been done before. Obviously, the common slump, air content, temperature, and compressive strength were measured. And additionally, we measured the rheological properties, the yield stress, shear thickening over increments of 15 minutes for a total period of 1 hour. We were utilizing shear vanes, as you can see in the photo, with the goal of producing mixtures with similar or better properties compared to the baseline shotcrete mixes. We also used calorimetry to understand the heat of hydration and the setting times of a given mix. So I know you all are waiting for me to spill the magic ingredients for how we got a mix that historically was limited to 20% slag replacement and bring it up to 70%. We had to tackle the stackability and finishability problem that arose from replacing that much cement. So we approached it from 2 angles. 1, by increasing the particle packing, and 2, by introducing a product that was hydrophilic. We tested multiple filler percentages, blended cements, and a colloidal nanosilica admixture, as well as different hemp fiber and cellulose fiber dosages. On the screen is one set of trials that we initially tested. With each new stage, we took lessons learned from the previous trials to optimize the mixtures and better replicate real-life conditions by adding delays to simulate batch, travel, and staging times based on where the concrete would be batched in the city and then where the location of the site was. The plastic properties of each mix were measured at the batch plant and then also measured when it arrived on site and after simulating 30-minute transport time. The rheological properties were also measured at 15, 30, 45, and 60-minute increments. The 28 days compressive strength results from the trials I had just shown demonstrated that all of the mixes exceeded the 35 MPa requirement. So you can see from the 28-day results. In order to verify the performance of the candidate mixes, the paste components were tested using TAM air and calorimeters for the heat of hydration over a period of 72 hours. You can see that the high volume slag mixes are a lot lower, well below the control mix. And I will show you the in-place measurements as well. Results from phase 1 of both suppliers were promising, suggesting that a high volume slag shotcrete mix was possible. We then selected the mix designs that had the highest potential for success, selecting those that performed similarly to the most similarly to the control mix. Those mix designs all included 70% slag and different combinations of colloidal nanosilica, hemp fibers, different percents of limestone filler, cellulose fibers, and macrofibers. Moving to phase 2, we had constructed a production-like mock-up to demonstrate the pumpability, shootability, and finishability attributes of the shotcrete mixes, simulating a similar length pump line as we could expect on site, which was about 60 meters of line. One trial was held at a ready-mix supplier's yard, and the other was held on one of our downtown Toronto projects. Samples were shot into wood test panels for hardened property testing, which we did compressive strength by taking cores, drying shrinkage by saw cutting prisms, boiled absorption and volume of permeable voids, and RCP as well. Non-standardized tests, we did a Beehive test. I forgot to mention we had Rusty Morgan come and help advise on a bunch of this extra testing that we've done. But a Beehive test was performed. This is a procedure in which the shotcrete mixture is shot onto a vertically oriented piece of plywood, laminated panel. And the performance is measured by recording the thickness of the material that remains adhered to the panel before sloughing or falling off occurs. The greater the thickness of the beehive before sloughing, the higher the degree of thixotropy of the applied shotcrete, and the greater the adhesion and cohesion. And then on the right here, we have what is called the buttress test, indicating the stackability. Sometimes people refer to that as the benchability as well of the shotcrete mix by measuring the thickness and height to which the shotcrete could be stacked without sloughing. In addition, a full-scale semi-adiabatic test with the shotcrete mixes was poured in order to verify the thermal performance characteristics and calibrate the thermal models on concrete works to later be able to add this to the thermal control plans that we had made for the self-consolidating and the conventional mixes. These cubes were 1 by 1 by 1 meter insulated boxes to represent semi-adiabatic conditions. And we had thermal monitoring devices installed at the center, top corner, and bottom corner. The data on the sheet on the screen is of the fresh property data that was collected for the two trials. Temperatures were controlled by the means of liquid nitrogen to limit the before shotcrete temperatures to 25 degrees Celsius. It was noticed that both slump and air dropped by about 40 to 60% after being shot using the contractor's preferred pressures. And it was also noticed that all but one mix performed better than the respective control mixes when comparing the Beehive test. As expected, the heat of hydration of the control mix quickly developed over a short period of time, peaking at basically 90 degrees Celsius. That's high. I mean, our max is typically 70 degrees Celsius. For the project, it was actually 65 degrees Celsius for the walls, whereas the two 70% slag mixtures significantly cooler, peaking at max temps of 66 and 63. These were the 4 final walls in one of the trials. In regards to the finishability of the 4 shotcrete mixtures, some mixtures stood out over others, with the heat of hydration developing quickly for the control mix, which is on the left. As expected, the finishing operations had to be formed relatively quickly to ensure that the surface could be troweled and finished smooth. The mix, which contained 70% slag and the nanosilica, showed signs of tearing at the surface and bleed bubbles or blisters due to, I think they prematurely finished it. And then on the other hand, the mixtures using the hemp fibers had a very, very nice finishability. The surface seemed to be enhanced due to the hemp fiber's ability to contain or capture the free water from the mix in a uniform gradient throughout the section. Again, the information on the screen represents the results from one of the trials. Beyond the plastic properties of the mixtures and their suitability for the use in these structural walls, the hardened shotcrete properties had to meet the requirements of CSA, the Canadian standard up here, class C1, and low shrink mix, and conform to the project specifications, which were even more stringent than the CSA. So the 28-day compressive strength results of each mixture was above 45 MPa, which exceeds the design strength of 35. The measured boiled water absorption values maxed out at 5.5% in 28 days for all of the mixtures, which is well below the maximum allowable of 8% based on CSA. To be classified as a class C1 mix, the rapid RCP value in 91 days has to be less than 1,500, where you can see all of these are way lower, the maximum 322. And then we also did shrinkage testing, and a low shrink mix is 0.04% each. I think the maximum for this was 0.032. So very good results. So this is very promising, suggesting that a high volume slag shotcrete mix will work if the contractor can properly shoot it. So we needed to test that. So the purpose of conducting a full scale mock-up was to ensure that the mix and shooting methods can provide full encapsulation of the heavily congested rebar details, monitor the heat of hydration, and as well as we wanted to use this to pre-qualify the nozzlemen and the shotcrete contractors. Here you can see both mock-ups. Let me go back. Here you can see that we did one mock-up where we had an overhead panel, and then the other one was just some really heavily congested rebar at a base detail. So you can see both mock-ups. This has the overhead and this just has heavy congestion at the bottom. There's one-sided formwork, bracing and reinforcing steel is installed. In the actual station structural wall construction, there's obviously not going to be formwork. This is just so that we could review the back of the wall. And then something else to note is we have some of the reinforcing is side-to-side lap splicing, and then we also wanted to test out front to back just to be able to get more consolidation behind the bars. Here's a picture of the full mock-up. This is also used to pre-qualify the nozzlemen and contractors to work on the project, which we found is very, very important to do. 2 contractors were invited to shoot identical mock-ups with the equipment and procedures of their choosing, but they did use identical pumps. There were noticeable differences between contractors though. One shot at 2 times the pressure of the other. One used a stiffer rubber tipped nozzle to promote the consolidation of the concrete in the back of the wall. Both contractors used a vibrator. One used a stiffer pencil vibrator, while the other one was noticeably less stiff and appeared underpowered. Both contractors finished the walls equally to a smooth finish. These photos are of the finished product. One deceiving aspect of Shotcrete obviously is that the finished surface is really the problem, and it actually what it hides behind can be the problem. Thermal monitoring was performed for both mock-up elements with placing temperatures of 25 degrees Celsius. The maximum heat of hydration can be seen to be just above 60 when shot into a 1.3 meter wall. 2 days after the mock-ups were shot and the Shotcrete had attained sufficient strength, the bracing and the forms were removed. This enabled the examination of the quality of the Shotcrete consolidation at the stripped form faces. Upon examination of the stripped faces, it was readily apparent that they were able to generally achieve excellent consolidation of the Shotcrete right to the back of the wall. There's one exception under that formed roof surface of the mock-up 1, which was a detail. It was just a little bit too difficult to shoot. There was about a 100 to 120 millimeter area of voiding, which we kind of expected. So they were, in the actual construction, they're planning on pressure grouting the top section. And then upon the examination of the stripped faces of the second mock-up, it was apparent that they were unable to achieve proper consolidation of the Shotcrete right to the back of the wall. While the side faces of the mock-up appeared reasonably well consolidated, the back faces did not achieve the same level of quality. It seems as though the nozzlemen were unable to get the Shotcrete to effectively penetrate beyond the back rows of the reinforcement and encapsulate it. You can see that there's reinforcement shadowing and large voids as soon as we stripped the wall, and then just taking a hammer to it. You could see that there was a thin, basically shell in many areas that were hollow once we hammered on it a few times. So the difference in the quality of the 2 mock-up walls opened our eyes to how contractor dependent the process is, and it can definitely be done right, but you need to have properly trained nozzlemen and inspectors for the application that they're going to be doing. And then to further examine the quality of the Shotcrete consolidation throughout the full thickness of the mock-up, we ended up extracting these 24 massive large blocks from the wall. It took weeks to just even get through the wall. So we only did it of one of the mock-ups. And each nozzleman was graded on the examination of the 4 sides of their extracted block and the window left behind in the wall. Beyond the exception that I mentioned earlier at the top of that roof section, there was only occasional small discontinuous voids at the congested areas, but overall the quality of Shotcrete consolidation and encapsulation of the reinforcement was excellent. Additional hardened properties were measured from the phase 3 shoot, which are required to develop a thermal control plan for the Shotcrete, mass Shotcrete as well. So we did coefficient of thermal expansion, splitting tensile strength, modulus of elasticity, and I believe I left Elliston at that point, but the team continued to go through this process and create a thermal control plan for them. And now I know that the project is now implementing the use of mass shotcrete in 3 of the stations, and I'm sure it'll be expanding into more of them. So in conclusion, this study has demonstrated that a 70% slag shotcrete mix design meets the structural, thermal, very strict thermal and durability requirements set by the specifications. 1.3 meter thick, heavily reinforced structural shotcrete wall can be successfully constructed using a 70% slag shotcrete mix with the right nozzleman and shotcrete contractor. The design team must understand the shotcrete contractor's work method statement and ensure that it matches with what was done to pre-qualify the nozzleman and what is being done on site. And a rigorous shotcrete inspector program is required to train the concrete inspectors to mitigate the potential for improper installation. They went through a full shotcrete inspector and nozzleman program after concluding these trials. And that is my presentation. If anyone has any questions. I think I kept it to 20 minutes because I thought there were more speakers.
Well done. Thank you, Stacia. That was a great presentation and really interesting and very impressive. Those huge walls, they're heavy reinforced and whatnot. I have a question, if you don't mind.
Yeah.
My question is QA QC program for like the actual production walls. Like, was there a plan for some like program of coring or program of some sort of non-destructive testing to get a feel for how well things are being consolidated?
Not that I know of, and sorry that I was less involved as I left, but I don't think there's anything on site right now, but they do have a million extra eyes that Rusty Morgan and a couple others from Alberta came to Toronto and delivered a full training program for the Crosslinks inspectors. So they had to go through, I think it was a 3-day training program to understand what to look for as the shotcrete is being done on site. And they're doing it in small bits until they're confident with the procedures.
Okay, excellent. And then one last question for me is in the actual production planning, what was the anticipated maximum height of a wall lift you guys were targeting approximately?
Oh, those were, I want to say 12 feet.
12 feet. Okay. And that's all going to be done from basically a nozzleman from one position. So he's going to cover, or he basically needs to be elevated up or change his nozzle position.
They built scaffolding systems. Yeah. So they had 3 different levels actually to shoot from.
Okay.